quick reminders before that. If you are participating in the room contest that starts right now for orientation in Lockpicking Village, if you're interested in CTF or deobfuscation, those are now online, as far as I know. Otherwise, this is Machinist talking about practical 3D scanning. Let's give him a round of applause.
Good morning, everyone. Well, nice to see all these bright beaming faces bright and early for LayerOne 2015. Whee! Thank you guys for coming out. My name is Chris, also known as Machinist. I'm from 23B Shop just down the way in Fullerton. And among other things, we've been doing a lot of 3D scanning lately. I thought it was a really cool thing and figured I'd come out here to show you guys a thing or two about it. So, yeah, welcome. Thanks for showing up. So, who is your daddy and what does he do? This guy's me. I do a bunch of different things, but mostly work in the 3D realm, and that's why I'm here to show you guys. So, when we're talking about 3D scanning, I think it's probably best that we set off some guidelines to be very specific about what we're talking about, because we'll introduce some new terminology here. 3D scanning, to put it in its most basic form, is some way to get a digital point cloud in your computer and manipulate it somehow. And with the typical file that you use for 3D scanning, the STL file format, it's exactly that. It's a big point cloud in Cartesian space with a triangle drawn between every 3 points and a surface normal pointing out, or which way is going out, which way is going in towards the model. And there's a couple other formats that you can use when you upload your 3D shapes up to like Shapeways or Thingiverse. PLY is a format that I've been using a lot of. OBJs are also pretty reasonably accepted. And one of the neat things with like high-end 3D scanning and complex 3D scanning is only in the last few generations of computing have the processors become powerful enough to handle the algorithms that are sorting through the big mess of data that these things are getting. I love this reverb too. So, what are you trying to do with 3D scans? Like, I've spent a lot of my career working with SolidWorks and building 3D shapes, but those are usually parametric. They're based on sizes and shapes and depths. Where 3D scanning, you're trying to get more organic structures or structures that are otherwise overly laborious to input in by hand, designating every size and shape of every object. So, to reiterate, one real useful thing to do with 3D printing or 3D scanning is to get these organic shapes or very large complex shapes that you would have trouble modeling any other way into your computer. So, a couple of tools of the trade we're going to be using here. I opted to go towards the low end for everything that I've been doing research on. About 6 months ago, Mr. Bot brought by a Microsoft Kinect that I've been doing the majority of my 3D scanning with. So it's a phenomenal piece of hardware that I can't praise it enough just because of its versatility, mostly because of all the software development that's been happening in the years since this piece of hardware has been developed. Makes it a phenomenal tool for doing 3D scanning on the cheap at home. So, a couple other considerations. One challenge with 3D scanning is that it's very processor intensive. So it does require a beefy processor, a bit of RAM. It helps to have a really nice graphics card. We're, again, running on the low end, so I don't have an optimized graphics card. The one that my software really wants is anything with CUDA cores, some specific NVIDIA cards, and in this case, we're running an ATI card, so it's not even doing any of the processing on the video card itself. It's all CPU based, so we'll be running at a lower frame rate, but hey, it will take what we can get. The computer was free, so it's kind of hard to argue with that. So once you have that 3D scan shape, inevitably you'd like to output that into the real world, and you need a 3D printer or big CNC machine to somehow get that shape into the real world. And how many of you guys were at Disconnect Camp recently? Handful, all right. So we were doing some 3D printing there, trying to make these shapes real with a MakerBot. We'll probably have the MakerBot up and running at the 23B after party if you guys are still around Sunday night. So something to look forward to. So this Microsoft Kinect, what are we looking at here? Interesting piece of hardware, it was just developed to be a little toy for your Xbox, and there's a phenomenal amount of crap packed into this box. And the one thing that they don't mention here on this diagram is there's a bunch of 6-axis accelerometers in this little Kinect here. So what's really cool is when we do a 3D scan, not only can you rotate the object around the sensor, but you can rotate the sensor around the object, and it can keep track of all the locations it's been and be able to stitch all of those depth maps back together. So yeah, it's a piece of hardware you can find at every local Kmart. I heard some interesting stories lately that you can find these at Goodwill for 25 bucks, even the really fancy Kinects. This is the older version. This was built in like 2007. There's a Kinect 2.0 that's squarer and boxier. One challenge with that. Hi, Freck. One challenge with that, the newer sensor, the 2.0, is it requires USB 3.0 connectors, so just make sure you have the proper bus for running that thing. And, we're looking at older hardware. It has a VGA camera in it, it's doing like 640 by 480 resolution, so pretty low end. 10 years ago it was pretty hot shit, but now, it's laughable. But what really makes the Kinect a wonderful piece of hardware is all the advances in the algorithms over the years. All of the research that's been put into occipital and in 3D coforms has really given us a lot of advancements with the ability to pick out the good data using algorithms rather than just relying on the hardware to force feed a bunch of useless information. So I'll be showing this a little later on. I have the Next Engine HD on loan from Null Space Labs. Thank you guys very much. It's been a lot of fun to play around with this. In contrast to what the Kinect was doing, the Next Engine here specializes in very high resolution, high detail scans, but you can't scan things organically. They have to be, perfectly still for, whatever time it takes for the laser to sweep across and figure out the depth map. And there's also a lot of manual processing involved with the scanning with this piece of equipment. You have to stitch together every single little piece, every single scan based on common points, where the Kinect, it makes that process almost automatic. So on the lower right hand corner is a piece of the robot chicken that ArcLight nearly won the HeboCon contest at SparkleCon a few months ago with, so that was a neat test. And just really hard to see on this shitty monitor, but on the lower left-hand side was a scan of a penny, and the right side was taking all the color. It was only showing the depth, and the scanner was adept enough to be able to see like the raises and the peaks and the valleys on the surface of the penny. So very, very high resolution. But like I said, it's a little tricky to work with. It doesn't like reflections as much. So again, how do these two pieces of hardware compare? And I'm terribly sorry for this crappy monitor. It doesn't quite do the difference justice. But there's like if the Kinect sensor was like a 20-foot scan, like it looks good from 20 feet away, the Next Engine was a 6-inch scan. The difference between 400 DPI and 40,000 DPI, phenomenal difference. But with that raise in resolution, you also have an equal raise in how much you have to fuck around to get the scans patched back together in a one continuous piece. I probably put maybe 2 hours of post-processing on the left-hand side, where the right-hand side, it was automatic. It took care of all the stitching together by itself. So you win some, you lose some. A couple other neat scanners I've seen out there in the wild. At the Build conference a couple of months ago, I was introduced to the structure sensor, which is pretty much the new hotness. It's essentially the same stuff that's inside here on this Kinect. It's just slimmed down, and it attaches to the back of your iPad, and somehow the processing environment is streamlined to work well with your iPad. So really cool stuff. Project Tango by Google is something you guys should probably be aware of if 3D scanning is your thing. They're starting to use, I don't know, this burgeoning technology to like depth map and texture map the entire environment as you're walking around with a phone. Kind of interesting implications if you think about like the long-term scope of, Google now knowing like the 3D shape of, every single walk space that you go by. It's kind of interesting to think about. So all of this talk so far has been on hardware. What about the software? One of the challenges with 3D printing and 3D scanning and just dealing with 3D shapes in general in the computer is there's always this tremendous stack of software you have to deal with. Not only do you have to know something like SolidWorks or SketchUp, but you also have to have some flavors of Blender and maybe ZBrush. Like where SolidWorks is dealing with like parametric dimension-driven forms, there's a more artistic side to the software, which is like dealing with clay, pushing and pulling little tiny bits. That's where you get like Blender type applications, or ZBrush. That's what they specialize in, is making more artistic forms than engineering forms. And what we're trying to do with this 3D scanner is bridge the gap between the two. It's like, hey, I got this little box. I need to kind of figure out something that fits in it. Okay, we should be able to 3D scan that quickly and get a form into the computer that we can then manipulate. So, like I was saying, we were focusing on the low end of the hardware, free, nearly free, very cheap stuff that was borrowed, given away, dumpstered. So I'm about $250 deep in this setup. $100 for the sensor itself, $150 for the nice open version of Skinect. The free version is fantastic. The only complication is that when you output scans using the free version of Skinect, it limits your model down to 5,000 polygons. So it looks a little blocky and max headroom-like, where the model over on the left-hand side was upwards of 1 million polygons. So much, much more detail, a little more processing power required to get the shape output, but phenomenal no less for $150 of software. So the majority of the scans I've been doing are in Skinect. It's pretty nicely tailored. There's not a whole lot of screwing around you have to do. However, since it's not the best developed software out in the world, it is a little bit buggy. It takes a little bit of time learning how to use it. But hey, luckily that's what I'm here for. I RTFM'd, so you didn't have to. So we're going back to talking about the software stack. Yes, there's a couple of different pieces of software that you have to use to get the shape from scanner to printer. And sometimes you have to use a few of them in combination, because Skinect, when it tries to patch all the surfaces together, sometimes it fails and crashes over and over and over again. But luckily there are a few ways where you can extract the raw data and manipulate the raw data in MeshLab to remove any of the dangling vertices, any of the stuff that makes the algorithms crash that's not necessarily apparent when you first start using it. So I'll get around to some examples where I show you what I mean between, noisy models with a lot of, dangling bits that could never be printed versus like one solid mesh that's continuous without any holes, without any errors that the printer can easily handle. One consideration for you guys who may not be 3D printer savvy is one challenge with getting these 3D shapes to the printer is what's called the slicing process. So imagine you have this 3D shape that, now it needs to be made on the printer. The 3D printer software needs to inspect each slice of that part and draw the perimeter around it and figure out the area in the middle so it can fill in the model with some print material. And you can imagine a highly complex 3D scan has, even if it has, one single error or one single vertex that's not connected to anything else, as the slicing software is trying to trace the outside, it suddenly divides by 0, or there's, one single vertex that isn't attached to anything. And these errors aren't clear, and you'll never find them in a pile of, a million points floating in 3D space. So that's what we need to be able to do, is clean up even the smallest little errors using automated fashions. Exclusively MeshLab is what I've been using, just because it's free, it works. That's all you guys need to know about that. So again, we're talking about the messiness of the 3D scans. With the Kinect sensor by itself, it has a resolution tolerance of plus or minus 1 millimeter, which may not be much. If we're talking about engineering terms, plus or minus 1 millimeter might as well be plus or minus a mile. But if we're just talking about getting like a 3D organic shape of, your friend's head, plus or minus 1 millimeter is close enough. But almost close enough, because one thing that's interesting about the human mind is its high ability to recognize patterns, especially like facial shapes. The smallest little change of the curl of your lips makes you not you, it makes you him. So when you get these messy 3D scans of, organic people-looking shapes, sometimes it's a little eerie, it sits in that weird part of the uncanny valley where you're like, oh, I realize I don't have the best complexion in the world, but damn, the scanner really, highlights that, when really it's just the inherent noise in the scanner, which we can remove with software. Yay, algorithms. Oh yeah, a little bit on MeshLab. Pretty interesting where this software came about from. A bunch of research facilities in Italy kind of put their heads together and said, hey, there's all these cultural artifacts that we should probably save somehow in digital form. And they put their heads together and built MeshLab. Lots of people have produced these crazy PhDs on the algorithms running in the background. And unfortunately, I'm not enough of a mathematician to be able to explain that to you. But if numbers are your thing, and matrix transforms and Laplace functions and stuff like that appeal to you, yeah, check out MeshLab, because that's all that's going on here. We're just dealing with large 3D matrix math. So I guess I got a little bit ahead of myself here talking about how to patch these surfaces back together. Like I said, I'll show you guys an example. Okay, I guess now I have to show you an example. Would anyone care to volunteer to have their soul stolen by the computer here? Anyone want to come up here and help me out? Come on up. Yay for the victim. Hi, what's your name? Joy. Joy? Joy. Nice to meet you, Joy. Okay, Joy, so what we need to do here is we'll take a nice little 3D scan. So one thing they mention in the Kinect manual is that the best depth of range for this sensor is about 36 inches. And what we need to do is set up a new scan based on some volume here. Instead of dealing with two-dimensional pixels, 3D scanners have to deal with three-dimensional voxels. And right now we're trying to calibrate the range of this sensor, because it has a minimum range of like 1 cubic meter and can see about 12 cubic meters in its maximum, which is about half the size of this room. So we're just trying to calibrate this on Joy right now and make sure we don't overscan or underscan. We want to get the maximum resolution possible. It's kind of hard to see, but it looks like we got about a 1 meter cube. Let's go a little less than that. All right. This is that fiddling around that you guys can learn from me without having to figure out yourself. Oh, there you are. I can see you in the box in real time. So the key here is to make sure that we have Joy encapsulated within this range. But like I was saying earlier, we can move Joy around the scanner or move the scanner around Joy. So the key here for you is to keep your body aligned, right? Keep your head straight to your shoulders. If you move that at all, you're get a really weird, like, warped face by the end. It'll be cool. Maybe we can do something with it. I I think the easiest thing for you to do is to like slowly twist to your left. You know, ever so about 1 RPM. And we'll see what we can do here. So you ready? The excitement. So when you're looking at all the green dots, that means those are pixels that agree with the other screens, the other screenshots. When you see red pixels, that's new information. One interesting thing to consider with this Connect is just the massive amounts of information that this sensor is taking in every second. Real trick here is that the software and the algorithms allow us to figure out like which details are related, which details are still good information. All right, that's enough. Thank you. Let's see how that goes. I think that'll be a good one. So yeah, massive amounts of data that this is taking in. One thing I always consider whenever I watch the Automagic happening here is how much of my lifetime I've spent watching status bars slowly move up a screen or little spinning wheels. It's tremendous. So okay, we got a decent 3D model here. Let's see if we can scroll in here. It looks like it goes all the way around. Very good. Nice. Big hole on the side, but that's okay. We can deal with it. And a big hole on the top, but we can still deal with that. So let's see. We'll go ahead and thank you for your help, Joy. Yay! First, I'll save this data in a pre-manipulated form. Just in case Connect has a hard time with it. But like I said, pretty Automagic. There's not a whole lot to it. So some magic processing here. There's a few commands. Watertight is the first command we need to worry about because I can't just print like a thin 3D shell. This has to be one continuous shape with volume and depth. So by executing this watertight command, the little magic squirrels start to process the STL file and figure out where the gaps are and sort of average the gaps to their closest neighbors. So it does a pretty good job of filling in these holes, and there's a lot of external stuff. MeshLab by itself actually does a better job of this. There's a single command called surface reconstruction Poisson, and I don't know, there's lots of good YouTube videos on MeshLab. They're all a bunch of like kooky Italian guys like talking you through it. That's how I figured out how that stuff works. But yeah, like I said, we'll see if Connect here can save the day. Oh, there it goes. Awesome. I like that. Sometimes it just crashes so hard right now. I'm glad I didn't have to fall on my face in front of you guys. Not that that's ever happened before. All right, yay, 3D color. So not too bad for a toy, right? So here's what I was talking about, that uncanny valley thing. Like you can see a little bit of eeriness in that shape. I'm sure if we had a better monitor, it would be even more eerie. But we'll go ahead and see if we can manipulate this in MeshLab at all, just so we can see a slight change in the surface and in the noise. So share, export models. Sorry, I got to talk to myself here. So yeah, there's a couple other functions inside of MeshLab, but really, or inside of Connect, but that's pretty much all you need to know. Watertight automatically colorizes things. You could probably rotate it or crop it to a plane, but it's fine. Automagic. When you do need the reinforcements, when you do need to bring out the big guns, that's what MeshLab is here for. So here's Joy in MeshLab. Very awesome. So very powerful piece of software here. It's a very strong rendering engine. Anybody familiar with the Unity gaming engine? Yeah, so the people that develop Unity also develop Mesh Lab, so same stuff. So yeah, it's going to be a little tough to see, but there's a lot of cleaning algorithms, smoothing algorithms. The smoothing algorithm I like the most here is Laplacian smooth. Laplacian smooth. I don't know. I've only ever seen that word written. So just one magic hit of the button, and you can't see anything. You just can't see that up here on the monitor. But it's a phenomenal difference, like from the 6-foot model to the 6-inch model. That's all the difference you need, because every little deviation in that organic shape actually shows up on the 3D print. And you can take it all out just at the flick of a wrist with Mesh Lab. It's phenomenal. Now, say we need to go the other way. Okay, Chris, great. You didn't show us anything. So, wonderful surface change there. Let's go the other direction. So, if you guys are a fan of max headroom, you might be a fan of this here. Simplification. Quadric edge collapse decimation. I love the names of all these commands. You guys are going to be tested on these later. So, every time I hit the apply button, there will be half as many polygons here in the entire model. I'm sure there's probably 700,000. That's what it looks like down here. Can't really tell. There goes that status bar again. I love it. Time for more scotch. It is way not too early in the morning for that, by the way. So 700 to 300,000, you can't really tell the difference, but you may be able to see the model starting to disintegrate now. Yeah, right. You could be your own like GoldenEye character. So yeah, that's 1,400 faces. It is kind of cool to see the simplified version of yourself too. I don't know. So in all the playing around I've done with this, I haven't found a whole lot of utility. Like the software is still ways off to be able to like automatically reverse engineer something. It's like, oh, I want to see what the exact size of this stage is. It can't figure out, the squares are 3 feet wide each. Eventually someday we'll get to that point, but that's still a bit of a distant target. And what I found this is mostly good for is just trinkets and showing off to your friends. Like, hey, you want a 3D scan of yourself that you've never had before and it looks really cool? Hey, that's great. And that's pretty much all that 3D printers are good for nowadays. Like, sure, there's a few engineering uses, but mostly it's for trinkets, right? Have fun. Let's go, make a silly object and waste a bunch of time and learn a few things. So I guess what I'm here trying to do is advocate this technology that we don't really have a specific use for it just yet. But the more that nerds like you and me play around with this, the more we'll find, novel uses for this. And, you also got to think to like Heinrich Hertz when, he discovered radio waves. He had no idea what people were going to use them for. He's like, I don't know, they're just there. Have fun, guys. And, that was 100 and change years ago. So anyway, I think that's about the majority of my presentation. I have many more demonstrations. I'll probably be set up somewhere during the rest of con just playing around with this so you guys can see it more in depth. Any questions at this point? I'm not sure why you would need to do that, but I imagine it's possible. That's all speculation, though. Bueller? It's too early in the morning for questions. Screw you guys. Well, thank you very much. And let those breakfasts sink in. Yay!